The first thing in section 16.5, and this is about the first half of this section, is how to parameterize a surface. So we've had to parameterize a space curve before, and I know I wrote in chapter 12 because that's where it first shows up, but it's not like this was confined to chapter 12. It showed up a whole lot in chapter 16 as well. So there's been a whole lot of this, right? The first half of chapter 16, it seemed like we had to do it over and over and over. Well, we've got a pretty good handle on it now. We got a space curve C. We can write out the parameterization where we've always been writing it this way with R and T as our parameter, and we get a vector function, and then we have a range of values for T, and we can parameterize a curve like that. But we could also parameterize a surface. It's a little bit more complex, which makes sense, right? You think, well, with a surface, that feels like it's an extra dimension, so we should have extra stuff to do. We do. We can still parameterize using R, our vector function, right? And we still have a vector function here, except now there are two parameters. So U and V are the two parameters. We got the ranges of U and V down there. So this is actually going to be a little bit tougher because there are some surfaces that are really awkward in one coordinate system and not too bad in another. And that, if there's anything to kind of keep an eye on, it's that. Like, what coordinate system feels like it's going to make sense here? And what I would say is, as far as the surface goes, kind of take what they give you in a way. And what I mean by that is how this one's a sphere. I would think spherical coordinates are probably going to match up pretty well. Or if you have something that's a cylinder or would easily fit inside of a cylinder, where you could kind of base it off of that shape and then kind of crop pieces of it off, then I would use cylindrical coordinates. So that kind of thing. There are going to be surfaces where there are multiple parameterizations that work. So like one in spherical coordinates and then maybe one in polar or cylindrical coordinates. Those are going to happen. And then there are multiple right answers. And I think we're actually going to see this very shortly. I think it's the second example, so it's on this page. But this first one where it's the sphere, and if you look at this, you go, okay, well, this has radius too. It seems like that's an important thing. And it is, because if we were going to switch to spherical coordinates, this is what you'd have generally. So that x is rho sine phi cosine theta and so forth. But we know what rho is. It's 2. So we can put it in, right? So there's 2 for rho. There it is there. There it is there. And now we've got a parameterization because our two parameters are the two angles. So they're phi and theta, right? Rho is not going to be a parameter here. It's just always 2. So that we don't have to worry about. All right, so we've got our two parameters. And then once we know what x, y, and z are, once we've got them written in terms of our two parameters, you can basically just sub them in, and you can see them down here, right? Here's r of phi theta, right? Those are going to be our two parameters here. So there's x, then here's y multiplied by j, and then here's z multiplied by k. And then you just have to get the bounds on theta and phi. Sometimes this is actually the hard part. Here we need the whole sphere so it's not so bad, because you think, well, for theta, you need to go all the way around the xy plane, so we should be going from 0 to 2 pi. And then remember from chapter 15 how phi works, where it's the angle away from the positive z-axis. So like if phi is 0, then you've got a vector that's pointing straight up, so parallel to the positive z-axis. And then if phi is pi, then you've got a vector pointing straight down. So that's the whole thing. If you go from 0 to pi, because that's from straight up to straight down, that would give you the whole sphere with these limits that are right here. Getting part of a sphere is actually harder than getting the whole thing. So that's what happens down here. It's the same sphere, but instead of the whole sphere, what if we just want the part that's above the cone, z equals the square root of x squared plus y squared? So you could actually set up the same parameterization here. It's just that your limits might be a little bit different. You still got to go all the way around in terms of the xy plane, right? Because you're basically getting a top piece of the sphere. It's almost like the sphere is sort of cut off and you're getting just like its cap, kind of. So you still got to go all the way around the xy plane. So the limits for theta are going to be the same. But this looks different. The limits for phi. Instead of going 0 to pi, this goes from 0 to pi over 4. And the reason for that, which I wrote over here in red, is that if you were going to draw that cone, the best thing to do would be, like if you were going to draw it by hand, I would set x equal to 0 and set y equal to 0 separately and just see what you get from there. And that should give you kind of a baseline for what to start drawing. And if y is 0, z is plus or minus x. So we're thinking of the top, right? Because it's the part of the sphere that's above the cone. So since I'm thinking of top, I'm thinking above the xy plane, like where z is positive. So I'm thinking of the line z equals x here more than z equals negative x. But I guess they would both kind of show up. But then when x is set equal to 0, then z would be plus or minus y. So you could draw them in as well, like z equals y, z equals negative y. But then specifically, if you just think about these, like z equals x or z equals y, the angle between either of those and the positive z-axis is pi over 4. That would also be true for z equals negative x and z equals negative y, by the way. But just for any one of them, so I picked this out. And if you drew it, like if you drew the xz plane, then what you're going to have for z equals x, I mean, it's going to go through the origin, and yeah, it's going to be at a 45-degree angle, or an angle of pi over 4. So angle of pi over 4 with the z-axis and an angle of pi over 4 with the x-axis, I suppose, but we're really concerned with the angle between that and the positive z-axis. So it's pi over 4. It's pi over 4 for all 4 of these. So, okay, well then that's going to be the angle between the positive z-axis and the cone. So that's really what we're trying to get, right? Because we're supposed to be above the cone. So by getting this angle, effectively we're figuring out where that cutoff is. So, right, like there's the intersection of the sphere and the cone where you have an angle of pi over 4 for phi. So that's what we're trying to do there. So that's the thing where I said, like, sometimes this is the hard part. Here it is, right? Like here, this part's easy because we already had it. But then down here, you got to cut things down a little bit on the limits for phi. And sometimes the way to reason through what you have to do is not straightforward. Like it's not the same process every time. It depends on what shapes you've got. So here it looks like that's what you'd have to do. Is you have to think, all right, cone, z equals x, z equals negative x, z equals y, z equals negative y, and go from there. This is also kind of an interesting example because you don't have to do it in spherical coordinates. Considering that example 1a is up here and that one's in spherical coordinates, I certainly would because that's going to be a whole lot faster. But let's say you were starting from scratch. You wouldn't have to do it with spherical coordinates. You could do this one with cylindrical coordinates. So how do you do it? Well, we know what x and y would be in cylindrical coordinates, generally, right? It looks like what you get in polar coordinates. And then we can say, well, this is the equation of our sphere, but then we can solve that for z. And since we're on the top part of the sphere, I'm not worried about the negative root here, right? That's why I just have the positive root, because we're on the top part of the sphere. But it would be this, right, if you solve for z. But then x squared plus y squared is r squared. So under the radical, that's really 4 minus r squared. So then all we have to do to figure out the limits on r would be to figure out where that top part of the sphere is going to intersect the cone. So that's what I figured out down here. And I said, well, the cone is z equals the square root of x squared plus y squared, but the square root of x squared plus y squared by definition is r. So I said, okay, fine, then the cone is z equals r. So we need where this z is equal to this z from the sphere. So I just set the square root of 4 minus r squared equal to r, square both sides, you end up here. So that would mean that eventually you would get that r is equal to radical 2. Okay, so when you're at the very, very top of the sphere, like the top point, up there r is 0, and you have to go out to where r is radical 2 because that's where the sphere is going to intersect the cone. So that gives us the limits for r. Right, that'll give us the range of values that r needs to cover in this parameterization. So r of r theta, which looks really awkward with the two r's meaning different things right here. I'm going to avoid this in the future. On the other examples, I just did it with u and v, when it was polar or cylindrical coordinates. But here I have it set up with r and theta just to keep it a little more conventional the first time. But this part looks weird. Anyway, that's x, that's y, that was z. And then to get that top part of the sphere, you still have to go all the way around in the xy plane. So you still got to have theta go from 0 to 2 pi. And then we said that r has got to go from 0 to radical 2. So that takes care of the parameterization in cylindrical coordinates. And both of these, like this one here and this one up here, they're entirely correct, even though they don't really look that much like each other. I mean, I guess they kind of do, but at least like the limits of theta are the same. But, and you know, there's a sine theta in here and a cosine theta in there. So there are ways in which like there are little similarities, but they kind of look totally different and they're both right. And sometimes this does happen. There are a lot of cases where there are situations where you could use a different coordinate system and it's extremely awkward. And like there's one that's not that bad and there's one that's crazy. But this is one where they're both like pretty sensible, right? Like neither of these are that insane to get. And sometimes that does happen. And in those cases, you know, either or, right? Whichever one you see first, I guess that's the way that you would want to go. The two examples on this page are pretty quick, but I just wanted to get a couple of other looks in here where the coordinate system to use wouldn't be spherical coordinates. So for example number 2, this word I think is the giveaway. Part of the cylinder. So cylindrical coordinates feels like that's the right move, and I would agree. The only thing that I guess is slightly different from how we've used cylindrical coordinates before, at least how we'd usually do it, is that this time the axis that goes through the cylinder is not the z-axis, it's the y-axis. So when we rewrite x, y, and z in cylindrical coordinates, the ones that are going to look like they're in polar coordinates are x and z this time, right? Because we got x squared plus z squared equals 16. And then y is just going to be y. So that's what we're going to end up with here. So if we write x as r cosine theta and z as r sine theta, we know what r is for that cylinder, right? It's the square root of 16, so it's 4. So I put a 4 in there and I put a 4 in there. But then what about y? Well, that's just y. It doesn't really have anything else that you could I mean, you could rewrite it. If you wanted to use a placeholder for y and say, I want to have y equal to u, and then you just have limits for u, I guess you could do that, but having it with just y is probably simpler. So now we've got our parameterization where our parameters are theta and then y. And then if I write out the surface with r of theta and y, then here's x, here's y, here's z. And then theta is going to go from 0 to 2 pi because we need to get all the way around the cylinder. Right? It's not like half cylinder or anything. We've got to get the whole thing. And then it said at the end here, between y equals -1 and y equals 3, right there, that just gives us the bounds for y. When we say, okay, well, y's got to be between -1 and 3, and that's basically it there. So this one is pretty short if you pick the right coordinate system. So since it says cylinder, cylindrical coordinates feels like that's the right call, and I would absolutely agree. And that makes this one nice and short. Example number 3, where now we want to parameterize an elliptic paraboloid. Okay, well, we have z written in terms of x and y, and you could use different coordinate systems here if you wanted to, but I thought, well, wait, if we've already got one of these written in terms of the other two, what if we just had these two be the parameters? That seems like it would just basically look like this. And that's what happens. So if you treat x and y as parameters, then if you were going to parameterize here, and I kind of wrote these out in an itemized fashion first, so then x would just be x and y would just be y, and then z is this, right? It's x squared plus 2y squared. And so we can write out a parameterization. We've got r of xy, so x and y are our two parameters. So there's x, there's y, there's z in terms of x and y. And I guess here you typically wouldn't write these out, If there's no restriction whatsoever on what x and y could be, usually you would just leave this part off. But I figured for completeness' sake, I could write it in. But there are no restrictions, like we don't want just part of the elliptic paraboloid, we want the whole thing. Okay, fine. Then we just got to let x and y be whatever. Right? So negative infinity to positive infinity for both. That'll give us the whole elliptic paraboloid. Some people do like to use placeholders here. There's nothing wrong with that. And I understand that logic where it feels like somehow you're not parameterizing if you're just using x and y. Like it feels kind of weird. If you want to do it, you can. Basically, you'd end up just calling x and y something else. So like here, if you call x u and y v, then you'd get that z is u squared plus 2v squared. And that'll work, right? So here's the parameterization in u and v instead of x and y. It looks exactly the same. But if you want to do it that way, it's not wrong. And I think when I first saw this, this was what I wanted to do because somehow this felt weird. Like it felt too simple just to call x, x, and y, y. But it is right. So either way is fine. And I guess in a way, this one is very slightly less work. The one with just the x and y in it. The next thing, this definition basically leads into surface area, but we need to know what one of these would be. So a smooth parameterized surface, that's one where the partial derivatives, so once we got the parameterization here, the partial derivative of r with respect to u and the partial derivative of r with respect to v, those are both going to be continuous, and the length of the cross product is not 0 on the interior of the domain. You can see why if you kind of cheat and look down here. If the length of the cross product was 0, we're not getting an area, right? You'd be taking the double integral of 0. Unless the thing that you're trying to get the area of is a single point, and it seems like that's not all that worthwhile, right? You'd know that'd have to be 0. Why would you do all this work? So, we want it to not be 0. Okay, so a surface area, if we have a smooth parameterized surface S where that's its equation right there, I guess this plus the limits for u and v down there, then the surface area of S, you can do it this way. So basically it's the double integral of the length of the cross product of the two partial derivatives. So you would get the two partial derivatives, then the cross product, then the length, and then you'd integrate this thing. So that's basically what we're going to do, although I guess sometimes you have to actually get the parameterization first. So that's the very first thing, right? The parameterization. So let's see, we want the area of the part of this plane that's inside this cylinder. Okay, well, because of cylinder, I'm thinking, okay, I probably want something in cylindrical coordinates, which this isn't a real cylinder shape, so maybe I can't have that exact thing, but part of this should probably be in polar coordinates though. So that's what we're going to do. So if we say that x is u cosine v and y is u sine v, where I guess instead of r cosine theta and r sine theta, just so we avoid the r being two different things when we write out this part down here. So x and y are going to be that because of this here, right? Because of the x squared plus y squared equals 4. And then you think, well, why am I not putting in a 2 for u? The reason for that is because since we're on the plane that's inside the cylinder, we're not just on the boundary, right? So we've got to cover ground inside the cylinder. So from where the axis is that goes right through it all the way out to its boundary. So u is actually going to have to range from 0 to 2 in order to pull that off. And then the other thing is we need a way to parameterize z. Well, z isn't in this, but it's in this. And I said, okay, well, based on this equation of the plane, then z would be equal to 4 minus x minus 2y, right there. But then if we have these representations of x and y, I can substitute those in. And so now this is what z would be when we make that substitution. And now everything, so x, y, and z, all in terms of u and v. So we've got our parameterization. And then we knew that u had to go from 0 to 2, right? Because we have to cover the inside of the cylinder this time. And then v, the angle, well, we've got to be able to get all the way around. So 0 to 2 pi, I guess, as usual. So then the parameterization, there's x, there's y, there's z, and then we've got u, so the thing that we would conventionally think of as being r, going from 0 to 2, and then v, the thing that's conventionally theta, going from 0 to 2 pi. Okay, next thing, get those partial derivatives. So partial of r with respect to u, right? That one actually ends up being pretty simple, right? You go, well, cosine v is the constant here, and then the partial derivative is just that. Same thing with sine v here, and kind of a similar idea with that thing, just with a couple of terms. And then partial of r with respect to v ends up being this. And then we need the cross product. So I wrote it out this way, where it's in the determinant form. And so there's r sub u, underneath is r sub v. So some of these things end up being really long. Like the first part of this, so you'd have I times the determinant of these four, right? So sine v times this minus u cosine v times that. And that's what this is. But then if you go, wait a minute, this term and this term are going to add out. And then you'd have u times sine squared v plus cosine squared v, but that's 1. So actually this thing in the set of parentheses here, this long thing, it's u when you simplify it down. And you can see it right there. Then the next one, once again, we've got stuff that's going to add out. And then here you end up with, well, I guess the negation of negative 2u, but that's just 2u. And then this one, you can see it directly. Once again, the cosine squared plus sine squared is going to help us out. We're just going to get u. So this actually won't be too bad when we get the length, right? I mean, this doesn't look that hard. It's not. So since that's what the cross product was, its length would just be the square root of u squared plus 2u quantity squared, so 4u squared, and then plus another u squared. So that's the square root of 6u squared, but you could write that as the square root of 6 times u. And so that's how I've got it down here when we're getting the surface area. So there's the length of the cross product of the partial derivatives, right? Square root of 6 times u. And then I put the limits of integration in here. So I have it set up to go du dv, where the limits of integration for u are 0 and 2, and then v 0 to 2 pi. I brought the radical 6 out front, and then you have a double integral where the limits are all constants, and then the thing that you're integrating, so the integrand, is a product of something in terms of u and something in terms of v. The something in terms of v is just 1. So this integral right here is just 2 pi, and then this one's not too bad, right? You integrate that, you get 1/2 u squared. Sub in a 2, that's going to be 4 over 2, so that's 2. So you end up with radical 6 times 2 pi times 2, which is 4 radical 6 pi. And that's the surface area here. Example number 5. So part of the paraboloid underneath that plane. Okay. Well, what I thought when I saw the x squared and the y squared, usually when that happens, you think, well, what shall I do here? Should I set this up in rectangular coordinates, which you could parameterize it that way, right? You could use x, y, and then x squared plus y squared. Although then parts of that might not be the simplest thing. It might not be as easy as this way. So when I see the x squared and the y squared, I instinctively think polar coordinates, or something that would involve polar coordinates, like a jump off to cylindrical coordinates or maybe spherical coordinates. But here, this is not a sphere-shaped thing. So I'm kind of thinking about it as though I'm going to do this in polar coordinates almost, because I'm also thinking, okay, well, this isn't a cylinder either, but it's more like a cylinder than a sphere, I think, if that makes sense. So if we're going to kind of use polar coordinates here, so r cosine theta and r sine theta, I used u and v again just to avoid the two r's meaning different things that are right next to each other. So I said if x is u cosine v and y is u sine v, then z, that's x squared plus y squared, but then that's u cosine squared v plus u sine squared v. You can factor out the u squared, and then it's u squared times 1, so it's really just u squared. Good, because now we've got x, y, and z written in terms of u and v, right? We've got the parameterization in terms of u and v happening, where then we've got to go around the whole xy plane to get this, so v's got to go from 0 to 2 pi, and then u has to go from 0 to 3 there's this constraint right here of being underneath the plane z equals 9. Because if u is 3, then you're going to get 9. Now that we've got the parameterization all set up, I think we can start going. So here it is, r of u, v, right? There's x, there's y, there's z. So we can get the two partial derivatives. So partial with respect to u, once again, not too bad. Neither's the partial with respect to v, honestly. And oh, look, we have a missing term. Well, that should make the cross product a little bit easier when there's a 0 in there, which there should be, right? There's no v in this. So yeah, you should get a 0 there. And then if we do the cross product, all right, well then if we go ahead and do that, then there's r sub u, there's r sub v. So let's see, then, yeah, for the first two terms here, this is going to be pretty quick, right? Because sine v times 0 minus 2u times u cosine v, right? So there's that. Same kind of thing in the second one. And then the third one, I guess there you do get both, right? Because it's that diagonal, that diagonal. But then you also get a 1 with the cosine squared plus sine squared. So you end up here, right? Once you use that trig identity, and then we want to get the length of this thing. All right, well, there's that first term, the negative 2u squared cosine v, there's that squared. This term, there's that squared, and then u squared is u squared. Okay, well, once again, we get the cosine squared and sine squared. So for the first two terms added together, that's really just 4u to the fourth, and then plus u squared. And I said, well, there's a u squared in both of these terms. If we factor that out, then we can bring that out of the radical and just say that that's u. So we've got u times the square root of 4u squared plus 1. So we're going to have to integrate that. So there it is, right? And then there's the limits for u, limits for v. And I said, well, there's no v in here, so I can write this as the product of two single integrals. So this part, once again, is just going to be 2 pi. And then here, in order to get this to work out, we're going to need an 8u instead of just a u, so we're going to need a 1/8 out front. So that's what I did here. I've got the 1/8 out front, got the 8 in there. And then integrating this thing, I guess you divide by 3/2 or multiply by 2/3. And then you've got the 4u squared plus 1 to the 3/2, double evaluated at 0 and 3. So this part out front I cleaned up and said that's just pi over 6. And then you get 37 to the 3/2 minus 1 to the 3/2. The 1 to the 3/2 is just 1, 37 to the 3/2. I think our book usually writes it this way, as 37 times radical 37. So that's how I wrote it here. And I guess you could multiply this out if you wanted to, but I figured that was far enough to go there. Example number 6. I wanted one where using spherical coordinates made sense, so that's why it's part of a sphere. And also, this happens to be one where we're going to know in advance what we're supposed to get. Because if you had to get the surface area of half of a sphere, you're probably not going to do all this work. You're probably going to do the thing that's up here in red. You're just going to use the idea that the surface area of a sphere is 4 pi r squared, and then you go, well, looks like r is 5, so we should get 4 pi times 25, so this should be 100 pi for the whole sphere, so half the sphere should be 50 pi. Yeah, that's what we should get as the answer, and this is much shorter, but to come up with one where spherical coordinates were obviously the way to go, I ended up with one where this is not the simplest way to do it. I guess in a way I almost wish I had been weird here and picked the lower half sphere just to have the limits on phi be different, but it's okay if they're like this. All right, so we're going to use spherical coordinates because we have part of a sphere, right? That seems like that would make sense. All right, well then the general versions are right there if you're going to switch from rectangular to spherical coordinates. And we know what rho is. It's 5 because of this, right? You go, yeah, that's rho squared right there. So, all right, well then we can write those out in terms of phi and theta. So there's a parameterization. We just need the limits or the range of values for phi and theta, or I guess theta and phi. So theta, we've got to go all the way around that upper half sphere, so 0 to 2 pi. And then as far as phi goes, because remember that's the angle between a vector and the positive z-axis. So you've got to go from 0, where you're pointing straight upward, to where you get to where, I guess, the bottom part of the upper half sphere would be. And that would be where you would have an angle of pi over 2. Right? It'd be a right angle between I guess, the bottom of the upper half sphere and the positive z-axis. I guess you could pick any vector that's in the xy plane. It has to be the angle between that and the positive z-axis, which is pi over 2. Okay, right? Because it's not going to be the whole sphere, right? If it was the whole sphere, this would be a pi. But because it's the upper half, pi over 2. Okay, then we've got our parameterization in terms of phi and theta. So there it is. And then we can get the two partial derivatives. A bunch of trig derivatives to get there, I suppose. Then if we get the cross product, then I think once again we're going to get some long things that are going to shorten up a little bit. But really it's just one long thing. It's just the k component here. So let's see. Yeah, okay, yeah, because of that 0. That 0 is our friend. That's going to help, right? So that's going to make the I and j components relatively short. And then the k component, yeah, it's that diagonal minus that diagonal. So yeah, that one's kind of big, but then you go, hey, look, cosine squared theta, sine squared theta. So it looks like once again, we're able to use that trig identity, and then this gets shortened up quite a bit. So then we want to get the length of the cross product. All right, well, squaring this right here, you're going to get 625 sine phi to the 4th, and then cosine squared theta. Similar thing here, and then here, I guess here we just have squared sine phi and cosine phi. All right, well then, let's see. Once we go down here, I factored out the 625 since it's in all three, right? You can pull that out of the radical because you can say, well, 625 is 25 squared. So there's the 25. And then for these first two terms, they both have a sine phi to the 4th in them. And then once you factor that out, you got cosine squared plus sine squared, which is 1, which is why this right here, once you pull the 625 out of it, it's just sine phi to the 4th power. And then you've got this piece down here that's just repeated here. And then I said, wait, there's something that's common to these, which is sine squared phi. So I said, okay, fine, factor that out. And then the square root of sine squared phi is sine phi. But then look at what you're left with under the radical. It's 1, right? Sine squared phi plus cosine squared phi. So this is really just 25 sine phi. Look at how nice that ended up being. It's a miracle. And then we're going to have to integrate that. So there it is, 25 sine phi. So I brought the 25 out front. I did my usual move of saying, hey, look, all these limits are constants and there's no theta in here. So we can break this up into the product of single integrals. And then this one, it's another 2 pi. And then we got to integrate this thing, but that's not too bad, right? You integrate sine to get negative cosine. Evaluate that at 0 and pi over 2. All right, well, then that's 0 minus negative 1. So it's 1 times 25 times 2 pi, which is 50 pi. So we get 50 pi. Okay, good. That's what we were supposed to get if we did it the short way. So it looks like everything worked out the way it was supposed to.